If we have a linear regression model with panel data and a error component model, then we know that it's important to try to distinguish between random and fixed specific effects. If we have fixed specific effects, only the fixed effect estimator will be consistent. While if we have random specific effects, pooled OLS as well as the random effects estimator and the fixed effects estimator will all be consistent, but only the random effects estimator will be efficient. So one procedure you can use if you want to investigate whether the specific effects are random or fixed is the Hausman test. The setup for the Hausman test is as follows. I have a stationary balanced panel with an explanatory variable. I have a linear regression model. I've only included one explanatory variable, but you can have more. You have a one-way error component model with individual specific effects. These specific effects could be time specific, and you could also have a two-way error component model. In the error component model, the mu-it errors are Gauss-Markov errors, so the explanatory variable is exogenous with respect to these errors. These errors are homoscedastic and not autocorrelated. Finally, we do assume that there is some individual specific variation over time so that the fixed effect estimator is available. The question we are focusing on is whether alpha I is fixed or random. So we already know the following. We know that if the individual specific effects are fixed, then only the random effects estimator will be consistent. That means that the fixed effect estimator will converge to a value that is not equal to beta 2. So in this case, they will converge to different values. If the individual specific effect is random, then both estimators will be consistent and they will converge to the same value. In this case, the random effects estimator is more efficient. That is actually all we need to apply a general test, which is called a Hausman test. What we do is that we simply estimate beta 2 using both the fixed effect estimator and the random effects estimator. Then we look at the difference between the estimates. If this difference is significantly different from 0, then that is evidence in favor of fixed effect. If the difference between the estimates is very small and close to 0, well then that's evidence in favor of random effects. So in the Hausman test, we simply set up the null hypothesis that the individual specific effects are random. That's the null hypothesis. If the null is true, we would expect our fixed effect estimate to be close to the random effects estimate and the difference to be close to 0. If we find that the difference between the estimates is significantly different from 0, then we reject the null hypothesis. We have then found evidence in favor of fixed individual specific effects. Doing the Hausman test in eViews is very simple. We specify our model. In this case, I'm explaining a log of milk production with the log of the number of cows and the log of feed. We estimate this model using a random effects estimator. So we set the cross section to random. These results are good if the individual specific effects are random. And to test for this, we simply go to View, Fixed Random Effects Testing, and Correlated Random Effects, the Hausman test. The test is a chi-square test under the null of random effects. This chi-square statistic will follow a chi-square distribution with 2 degrees of freedom. That is because we have 2 explanatory variables. So we can find the critical value from a chi-square distribution, or we can look straight at the p-value. If you use a level of significance of 5%, you should reject the null of random effects. That is, in this case, you should probably go with the fixed effect estimator. You can see that eViews presents the estimates of your beta parameters, both using the fixed and the random effect estimator. And the point is, these estimates are very different, then we reject the null. You can see that the problem is not with the estimate of log cows parameter. Those estimates are really close. The difference is not at all significantly different from 0, which we can see from this p-value. However, the estimate of the elasticity of feed will be significantly different if we use the fixed effect rather than the random effect, with a p-value of 0.002. The p-value of the Hausman test is a combination of the p-values of the individual parameters. The Hausman test in Gretel is equally simple. Just go to Model, Panel, Fixed Random Effects, log of milk is our dependent variable, and you have to estimate the model using random effects, just like in eViews. Click OK, and in Gretel you don't have to go to the menu to do the Hausman test. It's actually presented at the bottom of the results. You can see that the chi-square value is slightly different in Gretel compared to eViews. This is due to the fact that the sample size is pretty small. If the sample size increases, then the values from Gretel and eViews will converge to the same number.